Hello everyone. Today in this video we are going to discuss about articulation point. It is a topic of exploring graph chapter of analysis and design of algorithm subject. So let us understand what is articulation point and importance to identify the articulation point in our today's video. So let us start our today's video on articulation point. First of all, let us understand what is articulation point is. Suppose we have one graph and graph has a number of vertices and number of edges. So let capital G is a graph be a connected undirected graph, then articulation point of graph capital G is a vertex whose removal disconnects graph G, then this node or vertex is known as articulation point. For example, suppose this is the graph has a number of nodes and number of edges. As per the definition, if we remove any node of the graph and removal of this node disconnect the graph, then this particular node is known as articulation point. For example, if we remove D in this graph, at that time this graph will be disconnected, or we can say will convert into different two parts and divided into two different components. This is ABC is one component and EFG is another component. So this D is known as articulation point. Now what is basic purpose to identify articulation point, or why do we identify articulation point of any graph? If graph represents some network such as a computer network or any road network, then graph must not have any articulation point. If there is articulation point in computer network or any road network, and when there is a problem with this articulation point, at that time it creates problem to whole network. For example, in a computer network, this node is articulation point. There are number of nodes connected each other, and this node is articulation point. Once this node goes down, then whole network goes down. It means that there must not be articulation point in a computer network or any road network. Otherwise it creates some problem with a whole network. Once we identify the articulation point of the graph, then the solution is very easy. We have to just connect both the component through the node other than the articulation point. So for example, this is articulation point, then this both the component we have to connect through the node other than this articulation point. So for example, if we connect this both the node, suppose this node and this node, at that time there is no articulation point in this graph. Let's take another example. This is the example of a road network. Suppose there are number of cities, city 1, city 2, city 3, city 4 up to city 8, and these all the cities are connected through different roads. So we can reach from one city to another city by road. So for example, if you want to reach from 1 to 2, then there is a one path between 1 to 2. Same way, if you want to reach from 1 to 5, then there is a path that is 1 to 2, 2 to 4 and 4 to 5. So in this way we can reach from one city to another city. Once we observe this graph, or we can say this network, at that time we can say that the city 4 is a point through which we can reach from one part to the another part. It means that if you want to reach from city 2 to city 8, at that time we have to cross city 4. If you want to reach from city 2 to city 6, at that time we have to cross city 4. It means that from this part, if you want to reach from any city of this part to this part, at that time we have to cross city 4. Now suppose in some days there is a problem with city 4, and because of this problem we cannot cross city 4. At that time we cannot reach from city 2 to city 5, city 2 to city 7, or we can say we cannot reach from any city of this part to the any city of this part because of problem with city number 4. So that we can say this city 4 in our graph or in our network is known as articulation point. Once there is a problem with the articulation point, at that time your whole network will be broken into different parts and it creates some problem with whole network. It is known as articulation point. As we discussed, once we identify the articulation point, then the solution is very easy. We have to just connect one node of one part to the one node of another part. Or we can say in this example, we can say that once we create path between city 3 to city 8, at that time there is no articulation point in this graph. So the solution is easy, but to identify the articulation point is very much important. So the question here is how to identify articulation point. If we have one graph and if you want to identify the articulation point, then how we can identify the articulation point? To identify the articulation point, we have certain steps. Let us discuss the different steps to identify the articulation point. Step number 1, find DFS tree of graph and give DFN to each vertex. As per the step number 1, the first step is we have to draw one DFS tree of any graph and then we have to give depth first search number to each vertex. Step number 2, add back edges, those edges who are not present in graph, and the direction of back edge must be from greater DFN to lesser DFN. Step number 3, find out low of each vertex. We'll discuss in detail how we can identify the low of each vertex. Step number 4, if DFN of any node U is less than or is equal to low of any node V, then U is an articulation point. Here U is a parent node and V is a child node. We have to check this condition for every vertex except our root node. And root can be articulation point if it has a 2 or more than 2 child. These are the certain steps that we need to follow to find the articulation point of any graph. So let us discuss all the steps with one example so that you can easily understand. For example, we have one graph and this graph has a number of nodes and number of edges. So let us identify the articulation point of this graph. So we discuss certain steps and the step number 1 is find DFS tree and give DFN to each vertex. First step is we have to identify depth first search tree. So here we have to follow our DFS algorithm, that is depth first search algorithm, and we have to visit each and every node and at the end we can get DFS tree. So as per the DFS algorithm, we can start from any node. For example, we are starting from node number A. So suppose we are starting from node number A, then we have to identify the node which is directly connected with A node, or we have to identify adjacent node of A. So A has a 3 adjacent node, B, C and D. Among these 3 nodes we can select any node. For example, first we have visited A, then we are selecting for example B node, then we have to select B node. Now B has only one option, that is C. B has only one adjacent node, that is C, because A already visited. So we have to select next node C. So visit C node. Then we have only one option, that is D. So we have to select D and visit D node. Then we have a 2 option, either we can select E node or G node, because D has a 2 adjacent node which is still unvisited, that is E and G. So either we can select E node or G node. Suppose we select E node, then we have to visit E node. Then after we have only one option, that is F, so we have to visit F. Then again we have only one option, that is G, so we have to visit G node. Then G has only one adjacent node, that is D, but D already visited. So there is no any unvisited adjacent node of G, so we have to stop. Now this is our DFS tree. Now the next step is we have to give a DFN to each vertex, that is depth first search number to each and every vertex. Depth first search number is nothing but it is a number in the order in which they are visited. So DFN number is a number in the order in which they are visited. So first we have visited A, it means that the DFN number of A is 1. Then we have visited B, so the DFN number of B is 2. Then we have visited C, so the DFN number of C is 3. Same way, D has a DFN number 4, E has a DFN number 5, F has a DFN number 6, and G has a DFN number 7. So this is the step number 1. First step, that is find out DFS tree of the graph, then give DFN to each and every vertex. So we have identified one DFS tree and we have given DFN number to each and every vertex. Now step number 2, add back edges. So we have to add all the back edges in our DFS tree. So first of all, what is back edge? Back edge is an edge which is present in original graph but not present in DFS tree. The direction of this edge must be from greater DFN vertex to the lesser DFN vertex. So we have to compare this our DFS tree with our original graph and we have to identify all the back edges. So for example, this is our original graph. So compare this original graph with our DFS tree. In this DFS tree, we have to identify the edge which is present in original graph but not present in our DFS tree. So just see here, A to C edge is available in our original graph but A to C edge is not available in our DFS tree. Same way, A to D is present in our original graph but A to D edge is not present in our DFS tree. Same way, D to G edge is present in our original graph but D to G edge is not present in our DFS tree. These all are actually the loop so that it is not available in our DFS tree, but we have to add this all the edges as a back edge. So add this all the edges, but the direction of this back edge must be from greater DFN vertex to the lesser DFN vertex. So when we add back edge from A to C, at the time we have to compare DFN number of both the node. DFN number of C is 3 and DFN number of node A is 1, so that the direction of back edge must be from C to A. Right? So this dotted line indicates back edge and the direction is from C to A. Now add back edge from A to D, but D has a DFN number 4 and A has a DFN number 1, so the direction of this back edge must be from D to A. Same way, add back edge for D and G. So G has a DFN number 7 and D has a DFN number 4, so the direction must be from greater to lesser, so that it must be from G to D. So these three are the back edges of the graph which is available in our original graph but it is not available in our DFS tree. So this is our step number 2. Now step number 3. As per the step number 3, find out low of each vertex. So we have to identify low of each and every vertex of this DFS tree. So first of all, what is low? It is the lowest DFN number that can be reached from a vertex by taking one back edge. So we have already added different back edges. Using that we can identify low of each and every vertex. So let us identify low of each and every vertex. We are not going to identify low of our first node, that is A node, because node number A has a DFN number 1 which is lowest than this all the node. So we have to start from the node number B, that is our second node. Find out low of this node number B. As per the definition, we can use any back edge. So for example, if we move from B to C and C to A, at that time the A has a DFN number is equal to 1. So the low of B is equal to 1. Same way, find out low of C. we have two paths. One is C to A, in that we are using one back edge, or we can use another path, that is C to D and D to A. At that time again we are using one back edge, but we can reach to the A node, so that the DFN number of A is equal to 1, so the low of C is equal to 1. Same way, if we find the low of D, then using this back edge, for example D to A, and the DFN number of A is equal to 1, so the low of D is equal to 1. Same way, find out low of E. So as per the definition, we have to use one back edge. So here if we move from E to F, F to G and G to D, at that time we can reach to the node number D, and the DFN number of D is equal to 4. So the low of E is equal to 4. Now find out low of F. So for the F, we can move from F to G and G to D, then the DFN number of D is equal to 4. So the low of F is equal to 4. And G to D, that is one back edge, so we can say that the low of G is equal to 4. So in this way we can find low of each and every node. So for this DFS tree, we have identified DFN number to each and every vertices and low of each and every vertices except our root node. So now let us follow our last step, that is we have one condition, that is DFN of U less than or is equal to low of V, then U is the articulation point. So in this last step, we can identify articulation point based on this condition. If this condition is true, then we can say U is the articulation point. Here U is parent node and V is a child node, and that we need to check for every vertex of the graph except our root node. So for example, once we make pair of A and B, then A is a parent and B is a child. When you make pair for B and C, then B is a parent and C is a child. When you make pair for C and D, at that time C is a parent and D is a child. In this way we have to make a pair, but we are not considering here root node, so that we have to start from the second node, that is from B. So we are considering first pair, that is B and C. So B is a parent node and C is our child node. So let us check this condition for B and C. U is equal to B and V is equal to C. So we have to check DFN of B less than or is equal to low of C. Here DFN of B is equal to 2 and the low of C is equal to 1. So 2 less than or is equal to 1, the condition is false. It means that B is not the articulation point. Now let us check for a next pair, that is our C and D. Here C is a parent node and D will be the child node. So next pair, that is DFN of C less than or is equal to low of D. Here DFN of C is equal to 3 and low of D is equal to 1. So 3 less than or is equal to 1, again the condition is false. It means that our C is not the articulation point. Then check for the next pair, that is our D and E. Here D is a parent node and E will be the child node. So DFN of D less than or is equal to low of E. Here DFN of D is equal to 4 and low of E is equal to 4. So 4 less than 4, this condition is true. So 4 is less than or is equal to 4. So 4 is equal to 4, so the condition is true. It means that our D is an articulation point. So D is an articulation point. You can check for each and every other pair also. For example, our next pair, that is E and F. E is a parent node and F is a child node. So DFN of E less than or is equal to low of F. So DFN of E is equal to 5 and low of F is equal to 4. So 5 less than or is equal to 4. So the condition is false. It means that our E is not the articulation point. You can check for F and G. F is a parent node and G is a child node. So dfn of f is equal to 6 and low of g is equal to 4. So 6 less than or is equal to 4. So again condition is false. So in this way we can check for each and every pair of the graph, and once the condition is true, it means that our parent node itself is a articulation point. So in this way we can find the articulation point, and for this graph D is the articulation point. So this is all about how we can identify articulation point of the graph. So thank you very much for watching this video.